Welcome back once again. Today we want to quickly look at tau 1 space. In the last class we talked about tau 0 space, that for tau 0 space, X is said to be a tau 0 space. Topological space is a tau 0 space if if you have any two distinct pairs in X, so that X is not equal to Y. I know that now. Then there exists an open set that contains G. I got that now, such that your Y is not in what? Is not in tau. That is given us as what? A tau 0 space. Now, today, we talk about tau 1 space now. Tau 1 space. What does it mean? In tau 1 space, if you have a space like this, and then you have a point X that contains an open set G, and you have another point Y, a point Y also contains a point of H. So that is why we have what? A tau 1. This kind of space, and I find this called tau 1 space. And note that your X is not equal to Y. Then number 2, note, so that is when this concept is satisfied, it's called tau 0. And also note that your X is not contained in H. I mean, your Y is not contained in, your Y is not in G. Here, your X is not in H. So those are the conditions that satisfy under the tau 0 space. Now, when we talk about tau 1 space, we said a topological space S, I got it now, is a tau 1 space. I got this tau 1 space if given any pair, consider that if any pair, let's say distinct, any pair distinct points, let's call it X and Y in X. I know that X and Y in X. So each belong to open sets which does not contain the other. So that's the verse of tau 1 space. And what I'm trying to say is that if you are picking A is in, let's say you are picking X in G, be an open set, then I must be what? My Y must not be in G. And if I'm picking an open set that Y is in H, then X must not be in that H. So that is what is given us as what? These are open for tau 1 space. Then also, later I'm going to put this theorem. There's a theorem here which says that a topological space S, I know that now, is a tau 1 space. It's a tau 1 space if and only if every single thing subset, let's say of subset P, let's say which subset of P of X is what? Is closed. So that is given us what? As a result, that okay, a topological space X is a tau 1 space if and only if every single subset P of X is closed. So that is, if you want to prove it now, let's look at the proof now. Now, let's say suppose X is tau 1 space. Suppose that X is what? Is a tau 1 space. By definition now, what happened? And you are picking a point P in X. I got that. So now we need to show that the complement of that P, that is, don't forget that it closed. You know what we are closed set now. So the complement of that P is what? Is open. So that's our target now. Okay, what happened that if by X is tau 1 space now, don't forget that this set P here, singularity subset P of X is what? Is closed. Then for to show that it's closed, they have to show that the complement of this one must also be what? Be an open set. I got it now. So now let us assume that let my x be in this set. Let my x be in that set now. Then my x is not equal to p. Are you getting that? So my x is not going to be, that is by what? By definition of Taiwan space. Can you see that now? So that's by definition of Taiwan space now. So that is, if my x is not, that means that once I pick an x from here, it's not even equal to p. This is not equal to p. It's talking about there are two distinct pairs now in it, so which are not equal. So there exists, there exists open sets. Let's say open set G now. So when you now pick up set G here, let's say that G now relative to x, because for each of the points now, let's say that's what I open set for this G, such that you now pick an x in what? In that open set G, and but what? Your p, the two pairs now, your p is not in what? In G of x. How do you know that? So x, I can show that x is in what? In G of x, which is sub of what? P of this one. I hope you are following that. So that means that my x in G of is now a subset of this stability set of whom set I have here now. So now the next one is that, and then also, and what I can now say that s, this one is now the union of all the open sets that contains what? That contains x. All the open sets that contain what? That contains, such that my x is not in this. So that exists what? An open set is now the union of everything that gives us this one now, because it goes on that contain all the open sets that contain x now, which is here. So this implies that this one is a union of open sets, and what? And is open. And is opened. Then this one, this set P is what? Is closed. That set P is now closed. Now, the next one is that, don't forget that if and only if now. If now suppose that this is closed, this subset, single subset P is closed now, can we show that it's also a Taiwan space? Can we show that it's Taiwan space? Now, conversely, suppose this set P is closed for every P in what? In G. I mean in X, sorry. For every P in X now. That is in the topological space. Now, let's now pick A comma B in X now. With A not equal to B. Now, since A is not equal to B, I got that. This implies that there is a B in G in what? In that complement of A. Because that means that what? Implies B it was what? Must be A, because if A is not equal to B, then B must be the complement of that set A. I got it now. So hence I can pick what? This C is what? Is an open set. Open set containing what? Containing B. And but not containing what? Not containing A. Likewise, similarly, also I can pick for this one, I can pick that, okay, for this one equal to this, also I can pick that my A must also be what? A B complement. Can you see that now? So also my A is not equal to what? Or B complement is what? Hence, that is hence this set B complement is an open set containing what? Containing A but not containing B. Because that it has satisfied the two conditions of what? Taiwan space. That's right. So hence I can show that X is a Taiwan space. So you can show that X is what? Is a Taiwan space. I can see that. So that means the condition has been satisfied, then we have what? A Taiwan space. You can say that a topological space X is a Taiwan space if and only if every single subset this of X is closed. So that is a simple way for proving the topological space. Now, another one I want us to look at, another result I want us to check. Here is this. Let's check another result now. So let's check another result here now. Another result says that look at this result. Sorry? It says that every subspace of a Taiwan space is also a Taiwan space. Like what you did for Taiwan space also. Likewise, you can do the same that okay, every subspace of a Taiwan space is also a Taiwan space. So it is very simple as ABC. You can follow the same pattern with how we proved it. Every subspace of a Taiwan space is also a Taiwan space. That's very simple. Though, how do we solve? Let me just prove it for you now. Now, let's look at the proof here. We say that let this S comma tau be a Taiwan space. Can you see that now? And let y comma tau y be a subspace of this x tau. Let me put x also to differentiate that tau x space. I understand. So now we need to show that every single subset of P, that is to show, we need to show that every single subset of Y is what? Is a tau Y closed what? Closed set. I understand. Or you can say that Y removing this one is what? Is open. Is a tau Y open set. So you can actually prove it like that directly. That okay, if you can able to show that every single subset of this of Y is a tau Y closed what? Closed set. Or you can show that by the time you are removing the single set of P out from it, is a tau Y open set. So you can show that with them. It's very easy to establish that. Now, if you now assume that this is a tau Y open set, now we say that now since x comma tau x is a Taiwan is a what? Is a Taiwan space, because we are showing that was already a Taiwan space now. Other than that, it's a Taiwan space. Now, then I can say that my x plus that of P is what? Is tau open. How's that? Is tau not open. So, but it can be P in Y, be the result of X. Can you see that? The result of X implies that Y intersection what? X plus that of P. You are moving that one out now. Must give us Y slash what? Slash of P. So by definition of subspace, I got by definition of subspace now, you can say that Y slash this is what? Is a tau Y open set. So that shows that thus, you can say that thus Y comma tau Y is also a tau Y space. So that is how you can actually prove the theorem on that. So I hope you are following now. I think you are getting it right now. So it's very simple as ABC. Then, lastly, before we call it a day, you can actually show this that look at this. Okay, you can look at this one now. It said you can see that every finite, look at that result. Every finite Taiwan space is what? Is discrete. Is discrete. Every finite Taiwan space is what? Is actually discrete. Also, you can show that result that okay, if you have any finite Taiwan space now, then it must be what? A discrete space. Now, what does it mean by discrete? Discrete, don't forget that is topology defined by what? X and its power set. That is called discrete topology. Discrete topology, topological space. When your topology is given as this one now, so we have the discrete. But when your topology, sorry, when topology is power set, shows that you now have S over power set. This called discrete topological space. Topological space. So now, how do we show that if you have a finite Taiwan space now, it's giving what? It can give a discrete space. So I think you can actually work on that also. So if we're going to talk about today under the Taiwan space, next one we'll look at the audio space or Tau2 space. So thank you very much. Have a good time. Bye bye.